Yeah, so lately my team has been using a lot of AWS step functions, and I'm pretty excited to share a bit of what we've learned with you today. And as Nicole said, I'm not going to be paying attention to the Zoom window, so I won't see any chats that show up. I do have some time at the end that we can take questions, but feel free to just butt in. There's not many of us here, so I don't think it'd be very rude. So yeah, just chime in and let me know. All right, so jumping in here. A brief overview of what we're going to talk about today. So we'll just give a high-level overview of what step functions is real quick and what tools we have available when we're building them. And then we'll dive straight into examples. And these examples come straight from my team's uses of step functions. I have kind of obfuscated them and simplified them for presentation purposes, but nonetheless, they are real-world examples. So you can enjoy that part of it. Moving on here. So what is AWS Step Functions? It is a high-level orchestration service that lets you combine and coordinate other AWS services. And by high level, I mean that Step Functions value is derived from its usage of and integration with other AWS services, as opposed to something like EC2, which has more intrinsic value on its own. Step Functions is based on state machines and tasks. A task is a state within a state machine that represents a single unit of work that another AWS service performs. And a state machine is a group of tasks coordinated into a workflow. In addition to Lambda and SNS shown here, Step Functions also supports integrations with many other AWS services, such as these. We're only going to be discussing a few of these today, but if you happen to use any of these services for your work, keep those in mind as we're walking through the examples and think of how you could use step functions to integrate with those services. In addition to tasks, which call out to another AWS service to do a unit of work, step function has another type of intrinsic state called flows, which allow us to build more than just sequential workflows. I'll go through the list here and just kind of give a brief overview of what each of these is. The first is a choice flow, which is analogous to a switch statement with a series of conditionals, which allow us to build branching logic. And the next is a parallel, which also allows us to build branches that are non-conditional. So they just execute parallel branches unconditionally. The next is a map, which allows us to iterate over an array of items. Next is a pass or pass-through state, which is generally just used to transform data or is just a placeholder. Next is a wait, which obviously will just delay execution for a period of time. And the last two are success and fail, which both immediately halt the state machine execution and mark it either as a success or a failure. We won't use quite all of these today, but we'll touch on most of them. So next, we'll talk about how state machines are configured. State machines are configured with JSON, which is specified by a schema called the Amazon States language. This example shows a minimum viable state machine with only one state, which is a success state, which means that it will just automatically succeed. The root level of the configuration has two mandatory fields, start at and states. States is a JSON object where each key is a state name and each value is a state specification. The structure of this state specification will change depending on the type of the state. In this example, the success state doesn't require any additional configuration besides specifying the type. Start at is the initial state of the state machine, meaning that this will be the first state evaluated, and the input of the state machine will be passed as input to the state. Next, we'll start to walk through some more state machine examples, and we'll talk about how the different types of states are configured. So our first example is going to be a bit of a warm-up. We won't leverage step functions too heavily, but we'll get a feel for its usage. And our motivating example here is that my team has several ad hoc jobs that we use for reporting or downloading data from third parties on an irregular frequency. These jobs are implemented as Docker containers, which are configured to run on Elastic Container Service, or ECS, which can be started from the command line via AWS CLI. However, to start any ECS task, via the AWS CLI, you must supply as input the container you wish to launch and several other identifiers, such as the ECS cluster to launch the container within. And if you want your task to run within a VPC, which we do, you also need to know the subnets and security groups to assign to the container. Obviously, we don't want to have to type all this information on every invocation, but we can wrap all this up in a bash script that first queries for all of the necessary identifiers and then subsequently launches the ECS task. Alternatively, we found that you can bundle all this configuration into a simple step function. Let's take a quick look at the state machine definition. Here we have our JSON state machine configuration. We have the mandatory start at and states properties defined at the root level, and we have one state defined. This is a task state with the resource property specifying that we want to run an ECS task. In the parameters property, we have listed all the exact same configuration that was required to launch the task via the AWS CLI. For brevity, I have admitted many options that can also be used to configure the container, most notably, which is container overrides, which can be used to override the container's command property or to specify additional environment variables, which can be used, which both can be used to supply input to the container. Using step functions as a wrapper in this way to invoke our ad hoc ECS tasks has had some unintended benefits as well. Since the bash script solution requires some local setup, such as installing AWS CLI and Python and JQ and cloning our Git repository, and practically only developers were able to run these tasks or initiate these tasks. But with the step functions approach, we were able to invoke the task via the AWS console more easily than we can via the AWS CLI. This means that our team's data analyst is now able to run ECS tasks via step functions via the AWS console whenever they need to, and does not need to wait on the development team to start them. Another advantage is that we can change the implementation of this reporting mechanism without having to change how the report is run. If we decide that the report would be better suited for AWS batch or a Lambda function or 10 Lambda functions, we can change the step function definition without disrupting or retraining anyone that actually uses the step function. It provides a stable interface with a flexible implementation, somewhat akin to a REST API or any other API. Now that we've talked through a relatively simple example here with only one state, I think we're ready for something a bit more complicated. So let's move on to our next example. So our second example is polling, and I'll provide a motivational use case again. A few months ago, my team decided to, or not decided, well, we needed to integrate with a third-party API that is asynchronous. This API has a couple of endpoints. It has an endpoint to submit a request, has another endpoint to check the status, and yet a last endpoint to retrieve the results once the request is finished. Additionally, the documentation states that requests take a minimum of 15 seconds. And lastly, we'll need to post-process the results before we ultimately send the response to our end client. Now, traditionally, I would have solved this problem using a queue or multiple queues and background workers that pull items from the queue or perhaps put things back onto the queue or queues. But with step functions in mind, I believe we came up with a much simpler solution. Apologies if the step function definition here is a bit too to read, but rest assured, I will go through each of these in more detail. So I'll just walk through the step function definition real quick. So at the start, we have a task state, which invokes a Lambda function to submit a request. We then use a wait state to wait for 15 seconds, since we know that the request will take a minimum of 15 seconds. Next, we get the status of the request, and then we evaluate that status using a choice state. If it's successful, we wait a second and then repeat. Or if it's still pending, we wait a second and then repeat. If it's successful, we start our post-processing and then ultimately send the response back to our client. If it fails, we enter into a fail state and fail the state machine. I really love how the definition of this state machine reads very similar to the requirements that I had listed previously. We've been able to express nearly every component of the requirements as a distinct state with its own name, which means that when we look at it in this graphical representation here, it's very clear what its intent is. Now, we'll go ahead and just dive into each state and see how they're defined so we can get a feel of what step functions look like under the hood. And we'll start with our initial state of submit request.
Hey, Myles, quick question.
Yeah.
Are you generating that image, or does that come from AWS?
This comes from the step functions UI.
Cool. Thanks.
Yep. So you can go take a look at any of your definitions in a graphical way at any time, and you can export them to PNG, which I've done. Okay, so looking at the definition of the first one, this state is a type of task, similar to what we saw in our previous example where we invoked the ECS container, but the resource property has now changed to specify that we want to instead invoke a Lambda function. The parameters property specifies the exact function that we want to invoke. And the next property specifies which state should be invoked once the Lambda function is completed. Relatively simple. So let's move on to our next state, which is the wait state. Once again, this is pretty self-evident, but this is the type has changed to wait, and we've configured 15 seconds. And you specify that we want to go to get status next. Nothing terribly complicated here. Moving on to our get status. This looks almost identical to the first status type of task. We want to invoke a Lambda, and we move on to evaluate status once this has completed. Now, we'll get into a bit more interesting state here next with the choice state, where we need to evaluate the status. So this state has a type of choice configured with 3 separate distinct choices. Each one checks the status value returned from the previous get status state. It first checks if the status is still in progress, and if so, it proceeds to the wait 1 second state before subsequently checking the status again. The second choice checks if the status is succeeded, and if so, proceeds to the post-process results state. The last checks for failure, and if so, proceeds to the failed state. So this is really how we introduce, this is the key mechanism by which we introduce conditional logic into a state machine. And all of these choices are evaluated in order, and the first match to succeed is the branch that will be taken. Since the remaining states in the state machine are types that we've already seen, such as waits and lambdas, I won't talk to the rest of them in as much detail. But we have seen in this example how we can compose tasks such as lambdas and flows, and such as the wait and choice states, into a more interesting workflow. So next we'll talk about how we can extend this design by adding some retries. And to motivate this next example with the use case, our state machine has been in production for a while now and is running smoothly. However, we have noticed that sometimes the last state, send response to a client, is intermittently failing. We've diagnosed and discussed with our end client and concluded that the issue actually lies on their side. Their API has a bit of instability, which cause requests to fail intermittently. They are working on a fix, but in the interim, they have asked us if we could simply retry sending the response whenever we get a failure from them. Thankfully, this change is trivial with step functions. So looking at our previous state machine, we've zoomed in now on the state that is suspect, and we'll try to make a change here. To accomplish this, I've added a retry block to our state definition, which is, you can't see it, it's in the middle, delineated by surrounding white space. And whenever our Lambda responds with the error com.example.request failure exception, which if you are using Java Lambdas like we are, it will be the fully qualified exception name. And if it receives this error, it will then retry. And it will wait 2 seconds and then it will retry, which is specified by interval seconds. If it receives the same error again, it will back off by a factor of 2 and wait 4 seconds before retrying again. And that is configured by the back off rate. And this will continue until the maximum number of attempts is reached, specified by max attempts. And we have 6 specified. And it's worth noting that these are all defaults. If you don't specify these values, this is what you'll get by default anyways. So not only is it trivial to add retries to your states, your state machine, but we're also able to follow like industry best practices by using the built-in exponential backoff features of step functions. So next, we'll dive into how we can add looping to our state machine. And to motivate this next example with a small use case, the third-party API response has been enhanced, and it now returns a list of PDF document or document links, which we ultimately need to forward on to our end client. However, the documents from this third-party API are not fully trustworthy, and we believe it would be judicious to scan them for viruses before ingesting them into our system and sending them off to our end client. So let's take a look at how we can implement this. So to implement this, we're going to use a map state, which I've added here, zoomed in and highlighted, immediately before the post-process state. This will allow us to iterate over each document and perform an action. And in our case, this will invoke a Lambda function to scan for viruses. So let's take a look at each definition, or at the new definition. So this state is specified with the type map and the items path property. The items path property tells step functions which list of values or where the list is in the input that we would like to iterate through. The iterator property effectively defines a miniature state machine that runs for each item in the list. Within the iterator, we have one state, which invokes our Lambda function to scan for a virus. And lastly of note, we can also configure the map state to run iterations concurrently using max concurrency, which in our case is very advantageous because scanning for viruses can be slow. So we're able to scan all documents at once and process that faster. And also of note, if you set max concurrency to 0, it won't be infinite. I think there's a default value of 10 that you would get anyways. But max concurrency of 1 will iterate sequentially, as you might expect. So we only have one more example here to talk through. And we'll talk about nested state machines. And you may have noticed by this point that our state machine has grown quite large and has quite a few responsibilities. So luckily for us, we do have some options. State machines can invoke other state machines, which means that we can extract part of our state machine into a new state machine and invoke it from the original. I kind of liken this to the extract class refactoring that you might perform in an object-oriented programming language. And generally speaking, the most common motivation for performing the extract class refactoring is reuse. If you want to be able to reuse a part of a class or part of a function outside of its original context, you would have to extract it into a new place so that you could reuse it. Or perhaps it is easier to test in isolation from its original context. The same is true here. Smaller state machines with less individual responsibility are easier to test and can be reused by multiple state machines. Let's take a look. On the left here is our redefined original state machine. And on the right is our new state machine. I've extracted the first half of the state machine into a new state machine and invoked it from the original. Now, all the logic required to get a full response, polling included, is in the new state machine that was extracted and encapsulated so that it can be invoked and tested separately from the original state machine. Now, just as a warning, just like the extract class refactoring, I wouldn't necessarily perform or recommend performing this refactoring unless you need to. Like an additional state machine does cause additional indirection. So unless you really need it, it may not be worth it. So let's just dive into the definition and take a look. The state is similar to other task types, like the Lambda, but the resource property now specifies that we want to instead invoke another state machine. The parameters property specifies the exact state machine that we want to invoke, and the next property specifies which state should be invoked once the state machine is completed. So that actually concludes all of the examples I've prepared for you. I feel like we covered a lot of ground in terms of what step functions has to offer, but I'm really afraid that I've barely scratched the surface of step functions. I will leave you here with a few more interesting topics related to step functions that I hope you'll be inspired to research on your own. To name a few, local development. Step functions does provide a pre-built Docker container, which can be used to run your step functions locally, and you can use that to, deploy and test your step functions on your local machine before you deploy them to an AWS environment. I've personally never worked with that. I can't necessarily vouch for it, but it's really on my radar to get involved with testing those locally. I feel like it could, really increase sort of, test coverage, considering, all the facilities you have for building step functions. They really start to become code in and of themselves, and it would be nice if I had some way to test them locally in a unit test way without actually invoking them on AWS. And the next is input-output processing. I purposely avoided this topic, like in this talk, because it could be its own talk in and of itself. It's rather broad topic within step functions. You have so many facilities for which to manipulate the input and output of states and how they're piped between each other. And next is error handling. We did touch on this actually a bit with retries, but step functions also allows you to catch errors and handle them gracefully. You can catch an error and proceed to a handler or a fallback state, or you can fail the state machine if you catch a certain type of error. Next is X-ray tracing, which is really helpful for sort of diagnosing errors with your step functions. And it integrates, really natively with the AWS X-ray service. So you can trace a request that came all the way from your load balancer all the way through your state machine, and to any subsequent state machines or Lambdas that you invoke from your state machine using the same trace, which is really helpful. Next is step function service limits. So like many other AWS services, step functions does have some pretty strict service limits that you will probably brush up against if you use it for long enough, such as like execution history, payload size of your input, etc. And so it's good to be aware of them and how to mitigate their impact. Next is logging and monitoring. So if you have a state machine that does fail for any reason, it's nice to be alerted and be able to diagnose why. Step functions natively integrates with CloudWatch logs, so it writes all of your execution history to logs, and you can configure alerts based on that. And last, and perhaps most interesting, is human in the loop. So step functions does support a concept of callback tasks, which means that there's a special type of task that you can use that will pause execution of the state machine until a token is returned via the step functions API. There's a lot of different use cases for this, but the most common use case is if you need to build a workflow in which a human needs to intervene. In the context of our example, we could have used this feature if we wanted a human to review, every PDF document before we sent them back to run client and sort of do quality control checks on those. So we could have paused the state machine, had a human review, and our API would have had to let step functions know via a callback token that we were finished reviewing and we could proceed.